Hello, welcome to today's lesson on the motor effect. In our lesson today, we will begin by learning what the motor effect is, and then explore the factors which affect the motor effect. So far, we have explored the concepts related to magnetism and electromagnetism. You have learned about magnetic fields, current-carrying conductors, and how they generate their magnetic fields. You are also aware of magnetic flux density. Building on this foundation, we can now introduce the motor effect, which advances our understanding of how electric currents interact with magnetic fields to cause motion. Let's get started. To comprehend the motor effect, we need to consider a conductor that carries an electric current. When an electric current flows through a conductor, it generates its own magnetic field around the conductor. This is known as the magnetic field of the current-carrying conductor. We saw this especially when we explored solenoids. Now, what do you think would happen if we place this current-carrying conductor within an external magnetic field, such as the field between the poles of a magnet? Well, let's think. The magnetic field generated by the current-carrying conductor interacts with the external magnetic field. When these two magnetic fields interact, the result is either a squashing together or a pushing apart of the magnetic field lines, depending on the direction of the current and the orientation of the magnetic fields. On one side of the conductor, the magnetic fields combine, reinforcing each other and creating a region of stronger magnetic field. On the opposite side, the magnetic fields oppose each other, creating a region of weaker magnetic field. This imbalance in magnetic field strength across the conductor generates a force that acts on the conductor, pushing it in a specific direction. This force causes the conductor to move. The movement of the current-carrying conductor in the magnetic field is what we refer to as the motor effect. Let's pause for a moment and appreciate this. We've taken a simple setup which only involves electrical energy. We have a current-carrying wire which has its own magnetic field. We have then placed this wire in another magnetic field. This has caused the magnetic fields to interact, and the wire has moved. So through applying some simple tricks we've learnt, we have been able to create spontaneous movement. This unlocks the door to mechanical motion produced by electrical devices. This effect, the motor effect, is key to hundreds of appliances that have shaped the modern world. The magnitude of the force experienced by the conductor due to the motor effect is influenced by several key factors. The first factor is the current through the conductor. The greater the current flowing through the conductor, the stronger the magnetic field produced by the conductor. So a larger current results in a greater force on the conductor. Second, the strength of the external magnetic field, often measured as magnetic flux density, also affects the motor effect. In this case, a stronger external magnetic field exerts a greater force on the conductor. Third, the length of the conductor within the external magnetic field is another determining factor. The longer the portion of the conductor that is within the magnetic field, the greater the force experienced by the conductor. Finally, the relative orientation between the conductor and the magnetic field also plays a vital role. The force is maximal when the conductor is perpendicular to the magnetic field lines, ensuring optimal interaction. In contrast, when the conductor is parallel to the magnetic field lines, there is no interaction between the fields, and thus no force is exerted. Understanding these factors enables us to have greater control and efficiency in the design and application of electric motors. By optimizing each of these elements, we can enhance the performance of devices that rely on the motor effect. In today's lesson, we delved into the motor effect. We learned that this occurs when a current-carrying conductor within an external magnetic field experiences a force due to the interaction of its magnetic field with the external one. This force leads to motion, fundamental in electric motors' operation, which convert electrical energy into mechanical energy. We also examined the factors affecting the motor effect. These include the magnitude of the current through the conductor, the strength of the external magnetic field, the length of the conductor within the field, and the conductor's orientation relative to the magnetic field lines. Understanding these factors is essential in improving the efficiency and design of electric motors. In summary, the motor effect is a crucial principle explaining how electric currents interact with magnetic fields to produce motion, underpinning the functionality of various technological devices. Watch the rest of the GCSE physics course at Sophos Education.